Today, we have pleasure to have Mohamad Jouni as a speaker. But before diving into the main talk, I would love to give you a short bio of him. Mohamad Jouni received his Bachelor of Engineering degree in Computer and Communications Engineering from the Lebanese University in 2016, and his Master of Science and PhD degrees in Signal and Image Processing from Grenoble Institute of Technology and the University of Grenoble-Alpes in 2017 and 2021, respectively. Since 2021, he's been a postdoctoral researcher at Grenoble Institute of Technology. In 2019 and 2023, he was a visiting researcher for 10 and 6 weeks, respectively, at Tokyo Institute of Technology in Japan. His interests include computational imaging, tensor algebra, hybrid AI methods, applications of multimodal and hyperspectral data analysis, and technology transfer. And today, we will be talking about their recent work on multi-feature hyperspectral unmixing based on tensor decomposition. Hi, Mohamad. Stage is yours if you are ready.
Okay.
Welcome, Mohamad, and the stage is yours.
Thank you very much. Thanks a lot for inviting me to this talk, to this seminar. So I will be sharing my screen. Let's see, allow. If I do this. Can you see the?
Yeah, you can see it.
Perfect. So thanks a lot for inviting me to this talk. So this presentation is going to be about my latest publication related to a multi-feature hyperspectral unmixing based on tensor decomposition. In fact, this has been something that was ongoing during my PhD thesis. So it was supervised by my professors Mauro Dallamura, Luca Drumetz, and Pierre Comon. And then, so this is, yeah, just give me a second, that's stuck. Sorry. Okay, perfect. So to begin with, so what is an hyperspectral image? Basically, we have the consecutive acquisition of grayscale images based on a spectral consecutive spectral acquisition of grayscale images, which are basically rearranged in a third order. So it's basically a third order tensor. So this is what we would call a third order hyperspectral image, or HSI, where we have one feature mode, which is the spectral mode. In this case, so if we take one pixel of a hyperspectral image, it's a tube that shows a spectral signature of that point in the scene. And what we deal with in this paper or in this work is multi-feature hyperspectral images in which we represent a hyperspectral image with more than just one feature mode. So it could be, which could be like either a natural acquisition time series of hyperspectral images, or a hyperspectral image with filtered spatial features along that are arranged along a fourth modality, for example. So what is the problem of hyperspectral unmixing? It's a very popular problem in the remote sensing community, in which we try to unmix the scene or the feed to extract some features from the scene based on their spectral signatures. It's basically a blind or let's say source separation in the remote sensing or in hyperspectral sense. In this case, the most popular or let's say direct description of this problem is through the linear mixing model, in which we suppose that for each pixel in the hyperspectral image, we have a fractional summation of some of like pure materials, which we call n members. So each n member is a pure material which represents a pure spectral signature in the scene. So for example, this pixel could be 100% asphalt, this pixel could be like 50% asphalt and 50% grass, and so on. So what we see in this case is that this linear mixing model supposes that the matrix M, in this case, it's like we take the three-way hyperspectral image, we rearrange the pixel modes so that each pixel in this case is a sample of the scene, And so on the second modality here, there would be the spectral information, the spectral wavelength. And so we decompose or factorize this matrix into two matrices, one that contains the information on the pixels, and the other one contains the information on the spectral signatures. And what we hope to see is that each column in A can be rearranged into a matrix, which is what we see here. So this would contain abundance, the abundances or the fractional abundances of the spectral signatures that are contained in the columns of B. Okay, and so this is what we call the abundance map, and this is what we call the N member. So this is basically what we see in the matrix-based hyperspectral unmixing, or hyperspectral unmixing based on just one modality, which is the spectral one. There are two key features in the linear mixing model, which is that we impose constraints of non-negativity, so that we promote the physical interpretation of the components, and the other one is that we impose the abundance sum to one constraint on the abundances, such that each row in A, so each pixel representation in A sums to one, which means it's a fractional abundance of the N members that exist in B. And so as a visualization of this, we see that if the columns of B are put in a space, in a subspace, we have like 3 columns in a subspace, for example. So we have vector 1, vector 2, vector 3. These are the N members. What we see is that the pixels of M, so each pixel of M of the hyperspectral image exists on a simplex that is bound by these N members, because they sum to 1. And so the abundances in this row, for example, like describe the position of each pixel on this simplex. So this is more or less the introduction for hyperspectral unmixing in general. So our motivation to do this work is basically to enhance feature extraction and hyperspectral mixing based on additional modalities. Basically, this was the core of my PhD thesis back then. And so what we want is to conserve the multi-feature, multimodal arrangement of data as tensor. So we don't want to streamline all the features in one. So we don't want to deal with it as a matrix, because then B is like a mash of features altogether. So it is not interpretable. We want to conserve the low rankness of the data. This is more or less mainly described by the rearrangement of pixels. But then, if we rearrange the pixels, we are losing the spatial and for the spatial connectivity of pixels altogether. But for that, we can counter it by adding spatial information of small neighborhoods in order to conserve the low rankness. We will see that later on. Another thing is that we want to incorporate abundance sum to one constraint in tensor decomposition. This is not straightforward. In matrix decomposition, it's very easy because it's a direct summation of the N members. And tensor decomposition it's a bit difficult because we have additional matrix of factor matrix. We want to keep the flexibility to impose constraints on each mode separately. For example, if there is some constraint that we want to impose in third modality, say it's time or spatial features, etc. We want to be able to impose this constraint without having to mix the features together. And the other thing, the main problem was that we lack, at least at the moment, we lack a generalized interpretable framework for hyperspectral unmixing with multimodal features. So more or less, let's say that we have a hyperspectral image. We filter it based on some spatial information. In this case, we use some morphological features. So it's based on the size of a neighborhood and the brightness and scale of the connectivity of pixels altogether. We impose this kind of structure of hyperspectral image. For example, this is fourth order hyperspectral image where we use consecutive scales of the neighborhood and different brightness features. These are in the morphological context. This is called the closing, opening by reconstruction, etc. And then we use the tensor modeling and analysis where we streamline all the pixels, and then we have low rank data tensor. and then we extract the features based on tensor decomposition. So in this work, in general, we propose MultiHU-TD, which is multi-feature hyperspectral unmixing based on tensor decomposition. It is low rank. It is based on the canonical polyadic decomposition, which we will explain soon. And it incorporates the abundance sum-to-one constraint in an interpretable manner, of course. We provide the mathematical, physical, and graphical interpretation of this framework. And we provide analogies based on the classical, which is matrix-based techniques, which is more intuitive in this case. So I think most of us here are familiar with the canonical polyadic decomposition, so I will go very fast, at least with what is relevant to this work. So basically, the CPD reveals the tensor rank. The main feature of CPD is diagonality of the core tensor. In this case, it means that the columns in the factor matrices are formed of like triplets or quadruplets, etc. So there is no interconnection correlations between the columns of the factor matrices, and this is beneficial for blind source separation, and in this case for multi-feature unmixing, because we want the features to be separated. And thanks to this feature, CPD can also be represented in a different as the sum of rank 1 terms. In this case, each term here is the outer product of 3 vectors, and each vector is related to one of the modalities. For example, in this case, this represents a material in the scene that is formed of this abundance map, this kind of end member or extracted spectral signature, and this one, this kind of some third modal feature on along the third modal. It could be time, it could be spatial features. What we'll see later is that this represents, this factorizes or encodes the variabilities along the third modality. And so this is what we call, it's good for material extraction, because in this case, each rank 1 term here represents an extracted material represented as the outer product of 3 vectors. And so for the related works, first, this work was inspired by our previous work, which was about hyperspectral supervised classification. In this case, we were only interested in the vector matrix A, which represents the abundances. So what we saw in this case is that we can have a third order morphological hyperspectral image, or even we also tried it for a fourth order. So we have three modalities of features. So we decompose it, we compress it with CPD into a low rank representation with just 10 to 20 columns. And then we classify it using any classifier, and then we use. So this was supervised. We saw that it works better than the state of the art at that time. And we wanted to go further and explore the features in more of a blind way. So to see, does it work as an unmixing problem, and can we interpret it so that we can go further, maybe through learning, through other techniques. So what we saw is that there was already someone.
Yeah, I have a quick question. Thank you, Mohamad. I was wondering what is the rationale between the fact that, so you assume that each material will correspond to a rank 1 tensor. So is this motivated by some like a physical kind of property of the spectral images, or is it?
Okay. In this case, let's suppose that. So there are 2 ways to answer this question. It's a very good one. The first answer would be that we don't want to separate materials based on just one feature modality, which is the spectral one. Let's say, for example, I want to separate my materials into small vegetation fields, big vegetation fields, small metals. Let's say these are like the cars in the scene, and they are big metals, like these could be the rooftops of buildings. In this case, you would need an additional feature modality in which it describes this kind of small and big size of images. That would be, for example, the morphological modality. Let's assume, for example, on the top of a mountain, we have snow that melts with time, and then it comes back in winter, and then goes away. So this is some kind of a time variation. of snow or of a snow material that fades away with time and comes back. So we want to see this information as embedded in the factors. So this is an additional factor that we can use, we can exploit to better characterize the materials of the scene. Another motivation to do this was, I will show an example. These are in the appendix. So here, for example, if we have this kind of, sometimes hyperspectral images come in time series, so it's a natural acquisition. So we are not even the ones that enforce or impose additional features. So imagine that like mod 3 features are time series of hyperspectral image. If we streamline all the features together, we will obtain features like this. So this is a matrix decomposition of pixels by features. And it's barely interpretable. It doesn't. I mean, even subspace is meshed all together, so you don't have any meaningful features. While in this case, for example, we do tensor decomposition (CPD). So we have the 3 vectors A, B, and C. B represents the signature of a vegetation. So we can see here it's like a line of trees, small trees, etc. And the mode 3 index in this case, it is actually morphology. So what we see here is bright features focusing more on the small size. I will explain that later. So it's focused on small size features of vegetation. We will see that in later results where I can show you the small vegetation, big vegetation with real images. So more or less, this is the motivation. No problem.
Yeah, thanks.
No problem. Yeah. Actually, this is where it's exactly your question. It's why we wanted to go further and explore these features. And so we found that there was already a baseline to interpret this kind of decomposition, which is the extended linear mixing model, but this is in the matrix-based technique. Because in the matrix-based technique, you don't have additional information. And when you talk about matrix decomposition, you have a huge subspace of solutions, and you want to try your best to restrict it. But another thing is that there are variabilities in real scenarios that you can't model with just a linear mixing model because it's too restrictive for the data. So what is proposed in one of the works, which is Drumet's et al. And published in 2016. So Drumet is Luca, she's one of the co-authors of this work. What was supposed to add for each pixel, so imagine how many pixels we have in one scene. So for each pixel, we have an additional degree of freedom in order to model these variabilities. But then you have to add even more constraints to try to control this huge number of degrees of freedom. And so for each pixel, now you have a simplex. So before it was just one simplex for the whole data. Now it's for each pixel you have a simplex which scales. So this psi matrix is the degrees of freedom that we add on the problem to model these small variabilities in the scene. And then if we streamline each pixel separately, it's equivalent to saying that each pixel is multiplied by this vector, and then this vector scales the end members. So what we see is that the simplexes of each pixel are moving on the columns of B based on the scales that are present in psi, so on the degrees of freedom that we enforce on the abundances. So from here, we saw that there is a lot of similarities with the CPD model, which we will see very explicitly. And these are like related works that inspired this kind of situation. So, well, this is very wordy, but more or less, we have this kind of cost function to solve in order to do this CPD. So MultiHU-TD is based on solving an ADMM problem to do canonical periodic decomposition with 3 key constraints. So sparsity on the abundances to yes, beheshte. Please.
Yeah, sorry to interrupt you, Mohamad. So in your previous slide, I didn't give what was F. The first summation, yes, summation of FIBR.
Sure. Yeah. So here we have MI, so it's 1 pixel of M here, which is equal normally it's usually it would be summation of A, B. So it would be the summation of A or the summation of B. So what we see here is it's not A directly multiplied by B. So what is proposed in this case is to say that there is an, so for each pixel, there is a function of B, of all the B. So there is an Fi of all the B, and this Fi is what we suppose that models the variabilities at this pixel that come from real scenarios. There could be some nonlinear lighting conditions, some atmospheric conditions. So we suppose that it is Fi of the BR, no problem. And then sometimes we suppose that Fi, I mean, it could be nonlinear. There are many publications on that, like Hankel's formula and other atmospheric. Sometimes it's nonlinear representation of the n numbers. But to be able to draw the analogy between extended linear mixing model and the CPD, we suppose in this case that Fi is a scaling constraint on B, a scaling degree of freedom on. So what we suppose is it's AIR, BRI, but the BRI in this case, it's a scaled version of the n member BR for each pixel. So this is a degree of freedom that imposes for each pixel and as well as for each n number. So it's a lot of degrees of freedom. And this psi b is what makes that each pixel has now its own simplex that moves around the n numbers. This actually comes from. I will go back to the linear mixing model. The linear mixing model, since we don't have any scaling on B imposed on B, it's just one pixel, one simplex by the columns of B, in which the pixels of M exist because of the sum to one constraint. They exist on this simplex. It's imposed that they exist on the simplex. So this is what we see here when we give the degrees of freedom to everything we have as pixels and in members. So then this one pixel is like one simplex is now a simplex for each pixel that moves around the columns of B1, B2, and B3, so that it models the variabilities that we have in a real scenario. So to better, let's say, control this, CPD has a better representation. I will explain.
Thank you.
And no problem. Thank you for the question. So in this case, what we impose is both as all together the abundance sum to one constraint, the non-negativity on the factor matrices in order to impose to promote physical interpretation, and the sparsity on A to limit the space of solutions for the problem. And so for the ASC solution, for the sum to one constraint solution, what we do is that okay, so it's just an update that we have to do at each iteration that imposes that ensures that the sum of abundances at each row is equals to 1. And to ensure this, we have to play on this kind of where is it of the CPD model. Sorry, the CPD model. I don't have it here. In any case, because normally it would be a summation of AIR, BIR, and CIR. So what we do is that we say that the BIR equals 1 over CIR. It is enough to choose one row in B to verify that it is the reciprocal of C, alternate in the reciprocal in C, so that the summation of A at some point is equal to 1. And then what we do is we just do this update in the tensor and in the updates of the factor matrices to ensure the ASC solution. And what is left to do in this case is to solve the CPD as a whole with the other constraints. In this case, we refer to Wang et al. Actually, it's also explained in the paper. But we refer to Wang et al. For the ADMM implementation of to solve the CPD problem. And then it boils down to just an alternating optimization of sub problems of ADMM based on on each factor matrix. So for each factor matrix, we suppose that we solve for A, where B and C are fixed, and then we do so alternatively until convergence. Yes, Farzani.
How do you choose R here, the rank?
Very good question. In this case, we went by, how do you call it? Our reference to choose R in this case was the NMF. So it was a matrix-based selection. So for NMF, we know that more like not NMF, but more like PCA. For NMF or PCA, the rank of just the pure material was more or less 4. And so when we add more features, we suppose it's around 8. So that was more or less a trial and error selection of the rank. I will show later on that the experiments we do it with rank equal 4, and we also show with rank equals 8. So with rank equal 4, you are constraining the results very much. Of course, the error, the reconstruction error will show clearly how it goes. With R equals 8, let's say, you are relaxing the decomposition, so it shows you more features. But of course, if you go even further, you are overfitting, so you get a lot of noisy components.
Okay, thanks.
But I would, yeah. In this case, we chose an arbitrary value. We didn't go for any ground, like set in ground technique. Yeah. So this is more or less the algorithmic implementation of the framework. And so by solving this, we are looking at this kind of a result. So we have a tensor, we have what we call a frontal slice, and we have what we call a horizontal slice. So each pixel in the tensor now is a horizontal slice with 2 types of features. So it's a matrix of features. And each frontal slice here represents either the original hyperspectral image or a sequence, so a hyperspectral image at a timestamp, or a filtered hyperspectral image, or the original hyperspectral image if it's stored with its filtered versions. And then we have in the reconstruction the core tensor, the abundance factor matrix, in which each pixel here, it's just one vector that represents the abundances of the pixel that exists as a matrix here. We have the n numbers or the extracted spectral signatures in B, and we have the third model factor matrix, which represents the variations along the third modality. So along the third modality. So here the point is to draw the link between CPD and ELMM. What we saw in ELMM is that it is a pixel-based spectral variability degree of freedom. So for each pixel, we impose a degree, some degrees of freedom by the same number of vectors of n numbers and the same number of pixels. And the CPD, it is naturally based on the frontal slices. So for each frontal slice, or for each hyperspectral image or a variant of it, we have just one vector that represents these variations or these degrees of freedom. And on the other hand, in ELMM, it was for each pixel, we have this kind of vector. And usually the number of slices of frontal slices or variations of the hyperspectral image that we have is much, much less than the number of pixels. So the degrees of freedom that we impose in this case is a bit relaxing for the matrix-based technique and also less restrictive or less free. So what we see is that if a slab, so a frontal slice of the tensor, we call it T, 2 points means that choosing all the indices, equals A multiplied by diagonal. So imagine that this vector is now a diagonal matrix. A is multiplied by this, multiplied by the matrix B. So we can see it as A multiplied by a function of B. And we saw that in ELMM more or less similarly. In this case, we choose a TI 2 points K. It means that we take one tube that is a horizontal tube like this. So it's basically mathematically it looks like this. So we can see here the parallels between CPD and ELMM. The only difference is that here it's based on each pixel, while here it's based on each frontal slice. And so the parallels are the same, except that in CPD we have less degrees of freedom and a better representation of the model, of the variabilities that we impose in the third feature mode. So now that we are imposing abundant sum to one constraint in the tensor-based case, what does that mean geometrically and graphically and even for visualization? In this case, we know that the frontal slices have common factors A and B. So here, what we did is that we streamlined the frontal slices. So now we see each frontal slice. So each one of these frontal slices is now a matrix, and so each frontal slice has A and B as common matrices. And the psi here is this diag of CK. So each row of C is this diagonal matrix here from 1 to K. And so what we see is that the frontal slices have common factors A and B. Each frontal slice can be represented as a simplex. So if we say that A is fixed for each frontal slice, we know that there are only these R columns of B in the subspace. And then for each simplex, for each frontal slice, we have a diagonal matrix that scales these vectors. So then for each frontal slice, we have as many simplices as the frontal slices that move around this kind of n members, which are at the core of the scaled ones. Oops. A and B are independent of the third mode differences in the hyperspectral scene, because now we factorize the abundances in A, the spectral information in B, and what's left is that C is the one that encodes these variations on the third modality. One could even choose A and B separately. If we take out the psi or the C matrix, we can just multiply A by B, and there is just one matrix that represents the hyperspectral data without these variations. The rows of C encode the third mode variabilities, because since A and B factorize all the other information. And so let's see some examples of feature modalities. So what we picked was the patch hyperspectral image tensors. I will explain it, and the mathematical morphology hyperspectral tensors. In the patch case, it's a publication that was done by Miguel Viganzones in 2016. In this case, it's a conference paper, actually. Sorry. So the point was to try to compress features of neighborhood pixels based on just a neighborhood. So we take a neighbor patch like this, and we stream. So the third modality is based on just streaming the pixels that are next to each central pixel. And so what this means is that now we have a tensor where each pixel is correlated with its neighborhoods. What we did in the classification paper, the one that was before this work, is that we took. So we have the original hyperspectral image here, and we do transformations of this image based on the brightness. So on the left, we see the bright transformations. On the right, we see the dark transformations. And with each transformation, we take a neighborhood of interest. And in this case, it picks the neighborhood, the pixels. It filters the image based on information related to scale and brightness. And we streamline this kind of information here. The goal is to see what kind of features are streamlined in the decomposition, because in this case, we believed that with mathematical morphology, we can extract more meaningful features from the hyperspectral image. While with the patch neighborhoods, with patch tensors, we are not adding much information. And so we try to kind of represent this visually. So for patches, we think that two consecutive frontal slices are more or less coinciding in the subspace, because there is not much variations between or meaningful information on the third mode. While with morphology, we can see something like vegetation that is large, vegetation that's small, metal sheets that are small, streets that are small, etc. This depends on the number of factors that we impose on the decomposition. So to discuss this experimentally, we choose this real hyperspectral image, Pavia University. We also choose another one, but this is in the paper. So in this case, I will present only the ones on Pavia University. We also have a test on the synthetic hyperspectral images in the index of the appendix of the paper. So first, to compare between the linear mixing model, so the matrix-based, and the MultiHU-TD framework, we use R equal 4, which is enough for the matrix-based, but while it's restrictive in the tensor-based, it still shows the same, more or less the same features, except with a difference that with mathematical morphology we are able to highlight more features. So I will explain. We see here that NMF or the LMM model, linear model. So we have vegetation here. This is already explained by this feature here, by the spectral signature here. We have bare soil, so it highlights some information here that are actually bare soil in the image. We have metal sheets. These are metal sheets. It's like rooftops of some building. And here it says shadow. Shadow is because in this component we have a relatively low amplitude, so it doesn't appear low intensity, so it doesn't appear in the LMM model. While here the difference, okay, we see the bare soil. Its signature is over here. We see the trees, similarly to the one in LMM. We see the metal sheets, and we see even the shadows. This is because morphology was able to promote some degrees of freedom to show this low amplitude as high amplitude. It's because in C4, so this one here, it is giving the high amplitude. It factorized these information, it absorbed them in that degree of freedom, and was able to show it in one of the factors. So another thing, what we did is to now carry out patch and morphology tensor decomposition using rank equals 4. In this case, we see that the patch works exactly like an NMF. So it gives you exactly the same features with a key point that I will mention. So we see the same vegetation that we see in NMF. We also see the same bare soil component that we see in NMF. We see the same metal sheets component that we see in NMF. But one thing that is remarkable here is that there are two components that are the same, even visually and spectrally. In the third matrix, the surprise is that it equates each other. It tries to balance this kind of variation in the patches, because patches doesn't add a new information. It just makes like a 1 pixel shift of the image along the third modality. So the information is essentially the same. While in morphology, it's already what we saw before, since it's the same decomposition. We see that it adds a new information. So we were able to see shadows instead of replicating the, one of the components. Yes, Guillaume.
Yes, just a quick question. Can you remind what is so you have the patches here, and the other modalities is the morphological properties. So can you just remind how you construct that, this other modality?
Sure. So
this is okay.
Yeah. So for patch hyperspectral images, what we do is we choose a neighborhood. So either 3 by 3, 5 by 5. So let's say here we choose 5 by 5 neighborhood around each pixel. So what we have is in the tensor, we have the pixels streamlined here, vectorized.
Mm-hmm.
And then for each pixel, we have its neighborhood being... so we put the 5 by 5, so 25 pixels are now... The neighborhoods are now presented like this.
For the patches, this is clear. It's more for the,
at
least to me, but it's more for the other one. How do you... I'm not sure I understood here.
Okay.
Yeah.
Perfect. So in this case, let's say that this is my pixel. I will try. Can I? Oh, no, I cannot. Yeah. So let's say that this is my pixel here, and I apply opening by reconstruction with 10 pixels, let's say. So it takes with 10 pixels with this shape. So it takes a disk around this pixel, and what it does is opening by reconstruction. It darkens the areas that are smaller than this disk. Closing by construction, it brightens the area that is smaller than this disk. So if there is a dark area that is smaller than this disk and around this pixel, it closes it. This is closing by reconstruction. So it fills it with the brightness around it.
So it's like a data
opening is
augmentation. It's like a data augmentation kind of thing. You take the initial image, you apply transformation to it, and then you just copy this transformation into a new tensor, basically. Like yeah, okay, I see.
Yeah, you could. Well, I wouldn't call it data augmentation, but it works like this.
Okay, but the
So,
idea, you take the initial image
yeah,
and then you create a new modality by doing transformation of your image, basically, that are parameterized
exactly.
by some.
So, for
So
each
here
image
is the size of the. Okay.
So then on the third modality, from a spectator that is looking at the tensor like this frontally, I see that each pixel has some kind of neighborhood scale information variations, let's say, based on brightness and the scale of the neighborhood.
And so then what you were showing after on the real on the hyperspectral dataset was this modality that you were mentioning, like the result on the next slide.
Actually, I can show you. This is in the appendix. I kept it just in case. So in this case, I take one of the spectral bands of the image, and I show that the patch tensor. So this is 3 by 3. So we have from index frontal slice k equals 1 to k equals 9. So we have basically this is the same thing. If I zoom in too much, you will see that each one is just a shift, 1 pixel shift of each of the other.
Yeah,
literally just that. While in mathematical morphology, we can see that there are different kinds of scale, colors, brightness. Yeah.
Okay.
So this is actually this is what the tensor looks like. You see?
Okay, perfect. Thank you.
Yeah. No problem. I kept here a keynote, like the frontal slices are slightly shifted versions of each other, of the original hyperspectral image. While in mathematical morphology, the frontal slices represent physical spatial features. Yep. Let's go back. Yeah, and this is why here we see some features that are highlighted because they are the low amplitude, the relatively low amplitude is absorbed by another matrix, so it keeps it. You could see it here, for example, because it's a bit heavy to see it. But let's say that this C14 scale is small, so it lets B4 to be normalized to look like the others. You see, more or less. And then the other side, it amplifies it because of C24, but B4 is still B4. It's still the same vector B4, more or less like this.
Thanks.
So this is why patch replicates the components, while morphology does not replicate it as long as the rank is still within that of the CPD. These are just how close the spectral components are to the grounded truth. But there isn't much difference when the rank is very small. Well, in this case, it's when we use rank equals to 8. So here is where we expect that some of the features are going to be not only spectrally unmixed, but also either by size or by brightness, or if there is time, it can. The time is not presented here, but it's in the synthetic image in the appendix of the paper. So what we see is that. So remember here we had the replicated components. If you see at A2. So this is the patch decomposition, and this is the morphology decomposition. In the patch one, we have A2, A5, A6, and A7. They look exactly the same. And if you look at the B2, B5, B6, and B7, they are exactly the same spectral components. So these 4 vectors here. We have B3, I guess. So A3 and A1 are exactly the same. And we have A8. And the A7. So essentially we have 4 components. No, actually, yeah, we have 1, 2, 3. So we have essentially 3 components the same as here. We have 1, 2, 3 components, and the rest are just replicated versions. Because here we don't have intrinsically new information, but we have some replicated information. While in morphology, we have A1, which is a big vegetation field, A2, small vegetation field. So we have like the trees here, but here we see the field as a whole now. Here we have gravel. So basically, this is like the small bare soil areas here and here. We have here we have it says bitumen, but it's also the like between buildings and bare soil, but the huge areas. Here we have the metal sheets. Here we have very, very small. So you can see that they are dots, very bright dots. I don't know if you can see it. I would need to zoom in. These dots are basically the metals that are the cars, because I used some, one of the scales that I use is like 3 pixels. So it separates this kind of features as just the cars over there. And okay, there are some cars in the parking lot, etc. And there are 2 versions of shadow. One that is closer to trees, so it's shadows falling on trees or in vegetation fields, and the shadows that are falling are on bare soil and some artificial. Yeah, Farzani, I hear you. I don't hear you.
Sorry for interrupting. So,
No problem.
So the evaluation is overall qualitative. I mean, going back to
Yes.
Guillaume's question, before you do the factor, like before you have no idea what are the factors, and then you look at the factors to see which features they represent.
That is a very good question as well. In this case, it is good to note in the sense of unmixing, especially, we don't have any reference. There is no how to say. There is no solid reference for unmixing. Usually what we use is either dictionaries of pure materials that we have. In this case, it's the ground truth that we have that comes with the image.
Okay.
And we don't have, it is next to impossible to have a ground truth of the abundances, of the spatial abundances. So what we actually have, even if you see that this image that is used for unmixing has a spatial ground truth, it is actually things that are both done by the same time, either manually, that I pick this pixel, I say this pixel is 100% this or 70% this, or by imposing a linear mixing model on some image and then extracting these, and usually the community uses it as not the ground truth, but a baseline, which is why I presented the linear mixing model first to see that this is what I expect to see. It's as close as it can be to a ground truth, but it is not enough, more or less. So yeah, usually unmixing results are rather qualitative with some quantitative evaluation based on how close are the spectra, the extracted spectra, to the ground truth ones. And these ground truth ones are taken from dictionaries. So you have a dictionary, a database of spectra, pure material, and you try to study this kind of, it's called the spectral angular distance between vectors.
I see, thanks.
Yeah. This is something that has to be solved. It's an open problem for evaluation of unmixing problems, and basically even a blind source separation, more or less, has this kind of problem. It's a blind for a reason.
Yeah, it's the same for explainability and interpretability, so I'm not surprised.
Yes, exactly. So we rely on what we expect qualitatively, more or less, and see what we can gain. Yep. And so the last remark is that in the third factor matrix, we expect in patches it's basically rubbish, nothing that can be interpretable. While here we can relate when there are big materials, there is a signature to it. When there are small materials, there is a signature to it. So for example, in A8, since it's the very small materials, we can see that C8 has a high amplitude on 3 pixels neighborhood. Actually, 3 pixels neighborhood is at index 4 and 5. Yeah. And so on. So as a conclusion, we propose this kind of framework that is generalized, interpretable, both visually, geographically, and geometrically, sorry, and like in subspace format. We have the abundant sum-to-one constraint that we also incorporate and interpret. We conserve the low rankness of the data. We conserve the relevant neighborhood information if we suppose that there is a spatial modality. We explain mathematically, graphically, and geometrically these kind of correlations, analogies between tensor-based and matrix-based techniques. So it's an extension of the matrix-based techniques to multimodality. We stress the importance of using physically meaningful features, like what we saw with patches and mathematical morphology. As perspectives, so one would want to see like subspace representations of the factor matrices. That would go maybe to subspace learning, to manifolds, etc. Exploring other features of tensor decomposition, like block term decomposition, because CPD usually is constraining to the rank, while block term decomposition can relax a little bit the spatial features. Exploring other types of multi-feature representations. Don't know, there is some paper on multi-angle acquisition of hyperspectral images. There's semi-supervised classification based on dictionaries. And there's if someone would want to extend the study to multivariate functions, so not restricted to hyperspectral images, but multivariate functions in general. There's a lot of work on that with tensor networks. And then where to go from here, like subspace learning, machine learning, tensor networks for multimodal hyperspectral representations. That was part of the plans during the PhD, but then I went somewhere else. And thanks a lot for your attention. It was a pleasure.
Thank you, Mohamad, for the great talk.
Thanks, Mohamad.
Thank you very much. If anyone has any questions, please. Yes, Fazan.
I have a question. So I was thinking the whole time about the uniqueness of the solution. So is there like does your tensor analysis add something about the uniqueness? Because what I imagine, like LMM wouldn't be unique, the matrix factorization, but tensor factorization would be unique.
Yeah, very good point. I used to have a slide here which shows like advantages of using CPD compared to LMM. Indeed, the LMM is has a huge space of solutions, so people. Yes, Guillaume, thank you very much for attending. So you would have a huge space of solutions, and then you would have to add a lot of constraints to try to find the solutions that you want. With CPD, I did a lot of analysis on CPD uniqueness for this case, but you couldn't finalize the results. So the point is that you would assume it is unique. Yeah, I don't have a direct answer to this. It's a very hard problem, and it's still an open question. But you could how to say, you could assume it is kind of unique because what you do is you constrain the subspace so much, since you have a lot of features to explore, and you use a low rank decomposition, and in a non-negative situation. And there is a paper that says non-negative tensors always have a unique solution. They always converge or have unique solution. I forgot. I cannot give the reference directly because it's a bit blurry in my mind. So you could assume under this kind of constraints, like non-negativity, while also using the sum-to-one constraint, so you are still imposing a lot with a constraining rank. So it's not the full rank, but it's constrained one. So the solution falls in a global minimum, more or less. But,
okay, thanks.
Yeah, this was my assumptions that I used, but of course, it's not set in concrete.
Yeah, thank you.
Thanks to you.
Any other question? Thanks, Mohamad. It seems that there is no question. It was a pleasure to have you and to meet you. Thanks so much. Thanks so much for your great talk.
Thank you. Thank you.
Thanks.
Hope to see you again. Bye-bye.
Yeah, bye-bye.